This episode, we're talking exploding stars with Dr. Or Graur, an astrophysicist whose new book Supernova explores how these violent phenomena are key to understanding the secrets of the universe.
Hi, I'm Or Graur. I'm a senior lecturer in astrophysics at the Institute of Cosmology and Gravitation at the University of Portsmouth. And I study supernovae, or how stars explode. And I do this by conducting different types of experiments where I observe supernovae with different telescopes here on Earth and out in space. And besides supernovae, I also study other types of what we call transients. So things that weren't there yesterday are here today and will be gone tomorrow. All in order to understand their physics and how we can use them to study other types of physical or astrophysical phenomena.
Fantastic. Yeah, well, thanks for joining me on the podcast today, Or. I thought it was worth. I mean, we're sort of speaking today because by the time this podcast goes out, your new book will be coming out, which is called Supernova, and it's sort of a guide to this phenomenon. So I thought it'd be worth at the very start just sort of delving into what actually is a supernova. What happens in the run up to a supernova, and what is actually occurring within the event itself?
Okay, so the short answer is that a supernova is the explosion of a star. Going deeper into this depends on what type of star we're looking at. So the thing that really defines a star's life is its mass, how much stuff it's made out of. The more massive you are, right, the more stuff you're made out of, the more likely you are to end up exploding as a supernova. And again, depending on how massive you are, you will die as different types of supernovae. And for each one of these, the physics is a little different.
Yeah, so I'm right in thinking that not every star will end its life in a supernova. So a supernova is only the end times for certain types of stars.
Correct. So the way we understand it right now, stars that are more massive than about 8 times the mass of our sun will go through something called a core collapse supernova. Where in this case, so the way stars work is they're made out of gas, and this gas is very hot. And in the core of the star, that's where the gas is hottest, and it's hot enough to fuse one element into some other element. So your basic type of stars, like our sun, they fuse hydrogen into helium. And as they do this, they release light, which travels through the star and out into space, and that's what reaches us. And this also provides radiation and gas pressure to support the star against gravity, which is constantly trying to collapse the star in on itself. Once you run out of hydrogen in the core, there's no more support against gravity, and the star begins to collapse. As it collapses, it heats up, and it reaches a new point where it can start fusing helium into carbon and oxygen. Okay, and so a massive star will go through several of these phases, where each time it fuses a heavier element into heavier and heavier elements, until it reaches a point where the core is completely made out of iron. And at this point, fusion will stop. That's because if you want to fuse iron into heavier elements, you need to invest energy instead of getting energy out of it. And so fusion stops, and at that point, the star will just collapse. The core will as it collapses, all the protons and electrons in the atoms will fuse to create neutrons, and you'll get a baby neutron star. And as the neutron star hardens, it'll give out a small kick, and that kick will send out a shock wave through the rest of the star, blowing it out into space. So that's a core collapse supernova. For stars that are less massive than 8 times the mass of our sun, they won't go through all of these phases. They'll stop. They'll usually stop after their cores are completely made out of carbon and oxygen. And at that point, that core will shed its outer layers in a slow wind that will just slowly billow the rest of the star out into space. And you'll get what we call a planetary nebula. And that core, what used to be the star, we now call that a white dwarf. And that white dwarf will, if you leave it alone, it'll just stay there and cool down. But if you put it in a binary system with another star, then you can have some fun. And then we're not quite sure what the other star is or what exactly the physics are there. But if you get to a point where your white dwarf can steal gas from the other star and slowly grow in mass itself, then you can raise the pressure and temperature in the core of the white dwarf until carbon is ignited, and you get a thermonuclear runaway explosion, like an atomic bomb, but an entire star instead of just a few kilotons, and that will completely blow up the white dwarf. And so that's another option. Now, our sun, for all those of you listening in and worrying that our sun is about to explode, you don't have to worry about that. Our sun is still in the in the first phase, where it's fusing hydrogen into helium. It's been doing that for about 4.5 billion years. We think it has another 4.5 billion years to go until it'll reach the point where it goes on to fuse helium into carbon and oxygen. That's when it will become a red giant. That's the point where Earth might get destroyed. So if you want to worry about anything, worry about the sun becoming a red giant. And then it'll, once the helium is gone, it'll settle down, become a white dwarf, and just do nothing. But don't worry too much, okay? This is 4.5 billion years in the future. So
It's really interesting listening to all that. And what's really interesting is, well, I suppose what makes me curious is much of our understanding of the build-up and the process that causes a supernova and what's actually going on. Presumably, a lot of that is sort of based on theory, because do we actually get a chance to witness a supernova happening in real time and actually study it? Are we ever lucky enough to actually observe one, or is our knowledge of the processes based on our knowledge of chemistry and physics and built on theory like that?
So it's a combination of everything you just said. We observe supernovae all the time. We know how frequent they are, and so we know how many galaxies we need to observe per night in order to catch one. And these days we observe a lot more galaxies than we need to catch just one. So we find these days we find between hundreds and thousands each year. And when the Rubin Observatory will come online in a couple of years and start its legacy survey of space and time, then we'll be discovering about 10,000 supernovae every night. Now, once we discover them, we start what we call following them up, right? We know there's a supernova there now, and so we keep observing it. We take images, we take spectra, which is a different type of image where you break down the light into its constituent wavelengths. And when we do that, we can start probing the chemistry of what used to be the star that blew up. And we can see what kind of elements are in different parts of the what used to be the star, the gas that's now flowing out into space. And using that and our analysis of the observations, understanding what kind of energies we're seeing, the velocity at which the matter is being blown out into space, all of that, we can start piecing together what happened.
What do you think are the sort of the main ambitions and sort of ideas behind the study of supernovae? What does it actually tell us about the universe?
So, like I like to say in my talks, supernovae are the superheroes of the universe. I don't know if you know this, but both DC Comics and Marvel Comics have superheroes named after this. So DC has a superhero called Supernova. Marvel has one called Nova. They always copy from each other. The supernovae play a lot of roles in the universe. So first of all, they're the endpoints for many stars. And so if you want to understand how stars evolve, you want to understand how they die, then they create other types of stars in the explosion. Like I said, in core collapse supernovae, you get a neutron star at the end. In some types of supernova, of more massive stars, you get black holes. And this is how you get small black holes. It's all through supernovae. They shape galaxies. So if you get a lot of supernovae going off in one region of a galaxy, all that matter being blown out into space can combine together to give you just one big shockwave that just travels throughout the galaxy and carves bubbles into the gas of the galaxy, and sometimes even leads to the gas puncturing the galaxy's disk and just blowing out into space. One of the main things I would say is they create and disperse into space many of the heavy elements in the universe. Right. So I said stars fuse hydrogen into helium, helium into carbon and oxygen, and to silicon into iron, right, and so forth. If there were no supernovae, all of those elements would just stay locked into the stars. But once you blow up, all of that is thrown out into space. And the enormous energies you get in the explosion also give you even heavier elements. And those elements then pollute the gas in space. That gas will itself one day collapse to form new stars. And so those new stars will have more heavy elements, and the planets that are created around them will have more heavy elements. And that's how you get something like the Earth, which has an iron core, and has humans, which are made out of carbon and breathe oxygen, and create, computers with chips made out of silicon and so on.
So do you think it's sort of safe to say that without supernovae, planet Earth and human beings wouldn't exist?
I do, yes.
Given that they are the end of a star's life, does that mean that they're actually quite a fairly recent phenomena in the sort of within the context of the history of the entire universe?
No. So we think that supernovae started happening as soon as stars started being created. We haven't yet seen the first supernovae. We're hoping that we'll be able to do that with the James Webb Telescope, which was launched back on December 25th, and also with the new extremely large telescopes that are being built right now. We won't be able to see the first stars themselves yet, but we might be able to see their explosions.
It's absolutely incredible. I mean, is there any way of knowing whether or not very, very early astronomers observed supernovae?
Oh, we do know. Our earliest records come from China. From well, it depends how verifiable you want it to be. I would say the first concrete observation of a supernova came from China about almost 2,000 years ago, um, and the Chinese observations were very meticulous, and they were court astronomers. They surveyed the sky every night to look for anything in the sky that was new or that changed or did something interesting. And they did this for prognostication. They were looking for omens. This is because the way the Chinese empire worked, the emperor only ruled under the mandate of heaven. If bad things started to happen, floods, pandemics, rebellions, you could say that the emperor had lost the mandate of heaven, right? And it was time to replace them. And so the astronomers would look for those signs beforehand, and emperors would take note. And usually, what would happen is that at some point, an emperor would die or be replaced. A dynasty would fall, and the next dynasty would then sit down to write a history of the previous dynasty, and they would collect all of the astronomers' observations, and they would connect them to events. And so you have these very detailed records that say a guest star appeared in the southern gate on this date and hour, and it was as bright as something, and it was visible for the next 3 months, and then it faded away and disappeared. At the same time, a rebellion under General so and so was quelled in the north, but the Yangtze flooded and so many people died. And so those were the Chinese observers. They were followed by Japanese and Korean observers who used the same kind of system. And then during the medieval Islamic era, we get similar observations spread throughout the Middle East, Europe, and Northern Africa. With some observations made by medieval Europeans as well, not as much, not as detailed, until we get to the Renaissance. And then you have Galileo and Kepler making very, very detailed observations as well. And I will say, because this is interesting, all of these observations are still useful to us today. We still study them. We still try to connect between those historical records and supernova remnants that we find on the sky. And we can actually take those records, written in whatever language, not written in today's mathematical jargon, and we can translate them into astrophysical observations that we use today, and we can analyze them, and we can say that was a type 1a supernova, and it was this luminous, and it was of this type and lasted so long. Which I think it's amazing, the fact that we can still communicate with our forebears 2,000 years ago.
Yeah, that is really, really cool. And I love the idea that you sort of have to translate it from their understanding with how the heavens worked to your sort of current, method of understanding the universe. When you were writing the book, When you sat down to write it, were you aware that it would sort of also turn into a sort of history of astronomy as well as a sort of astrophysical guide to exploding stars? I suppose in a way, if you're talking about a phenomena, you also have to analyze the way that human beings have before you have analyzed that phenomena.
So I always intended to have a chapter on history, because I think that in order to understand what you do today, you need to understand what came before you. But I was surprised at the depth and breadth of how supernovae were studied throughout the world over time. And in the end, I actually wrote two chapters on history. So I have one on ancient history and one on the modern history, which is also very fascinating. And it led me to explore more of the history of astrophysics in general. And just how global and interconnected everything was from the very beginning.
Yeah, it's incredible. And isn't there a mass extinction event that you talk about as well? It happened like millions of years ago, and they think that that might have been the result of a supernova.
So that's something that I learned about only while reading the book. While writing the book, I didn't know about it before. So there's a specific subfield that studies this. What they do is they look at concentrations of a radioactive isotope of iron called iron 60, which has a half-life of I think it's a few million years. The main point is that it has a half-life that is shorter than the current age of the solar system. So any iron 60 that was in the solar system when it was created has already decayed away. Okay, so any iron 60 you find today had to have been deposited or created at some later stage. And what different groups have found is that you find iron 60 in the Earth's oceans. You find it on the surface of the moon, in lunar rocks collected by the Apollo missions, and um, and from those concentrations, you see that that iron 60 had to have been deposited on Earth, on the moon, between 2 and 3 million years ago. And coincidentally or not, there is an extinction event 2.6 million years ago at the boundary between the Pliocene and Pleistocene eras. It's not one of the mass extinction events, like the one that killed the dinosaurs. It's still one that killed, if I remember correctly, about a third of all types of marine animals on Earth. So, I mean, every extinction event, is still an extinction event. And if you look at where the sun should have been about 2.6 million years ago, you see that it should have been in an area where there are young stars. And so you start building a story here where about 2.6 million years ago, the sun went through an area of the galaxy where there were a lot of young stars, and some of those young stars, around 10 of them, exploded as supernovae and rained down iron 60 and other elements on the solar system, which settled down here. And here's where things get a little iffy. The radiation from the supernova may have affected Earth's atmosphere, may have stripped away part of the ozone layer, or affected it in a way such that life on Earth was not as shielded as it should have been from UV and other harmful types of light. And maybe that's what happened. Now, I'm saying this is still very iffy, because this is where this is where you go from observations to theory. And it's not quite clear what the supernovae could have done. But it's still, when you get these coincidences, you have to ask yourself, why, and what could have happened, and how the two things connected.
Yeah, there's something really satisfying about that, isn't there? When you're sort of doing that sort of detective work, even though it's millions of years ago, you can actually do that detective work and find that the pieces fit into place. It's really satisfying, sort of hearing you describing that. There was something you mentioned though, which was the a type of supernova called a Type 1a supernova, and I was definitely going to ask you about that because in my sort of understanding of it, they produce something called a standard candle, and I was wondering if you could explain that because I personally find that aspect of supernovas really, really interesting.
Yeah. So type 1a supernovae are the kind of supernova where we think we have a white dwarf blowing up. And when you observe type 1a supernovae, you find that many of them, they rise, all supernovae rise to a peak and then start to decline. But the type 1a's um, do this in a very predictable and regular fashion, so that they peak at roughly the same luminosities. And not only that, but the ones that take longer to rise to peak and fade away, those are always more luminous than the ones that take less time. And so you can use that to calibrate these supernovae and compare ones that are far away with ones that are nearby. And then you can say, oh, I see a supernova in Andromeda, and it's this bright, but I can only also see how it brightens and fades away. And so I can compare it to a supernova in the Milky Way galaxy that rises and fades in the same manner. And this one is in my backyard. I know exactly how far it is away from me. So I know not just how bright it is, but how luminous it is. All right. Luminous, it means how much light it actually outputs, whereas brightness depends on how much light we get. And then I can compare the supernova in the Milky Way to the one in Andromeda, and that way I can get a distance. And so that's why they're called standard candles, and that's how we use them to measure distances to faraway galaxies. And they became really famous at the end of the 90s, when two groups of astronomers used these type 1a supernovae to measure, as I said, distances to faraway galaxies, originally in order to measure the how fast the expansion of the universe was slowing down. Okay, that's what they expected to see. Instead, what they found out was that the expansion of the universe was actually accelerating. And in order to accelerate that, they had to invoke something new in cosmology. They had to say, oh, I need something to overcome gravity at cosmological scales. I'm going to create something, and I'm going to call it dark energy. Okay, and dark energy is one of the big unknowns in today's astrophysics, and a lot of people work on it. It's why I got into the study of supernovae, and we still use them this way today in order to study dark energy. So there are many surveys out there. The Dark Energy Survey, for example, which discovered thousands of Type 1a supernovae, exactly to do this, to try and get more information on what exactly this dark energy might be.
I can see why you got so interested in supernovae and why you're so passionate about them, because it's almost like they're just key to understanding, just basically key to understanding the universe, but also key to understanding the history of our own planet.
And it also exemplifies one of the core things about astrophysics, right? Where we use physics to understand how the universe works, but then we also use the universe to understand how basic physics work. right? So I study the progenitors of supernovae. I try to connect between all the various types of supernovae that we see and different types of stars. And I do that in order to understand the physics of the supernovae, right? How they explode. But at the same time, we're using supernovae as tools in other experiments, right? We use them to measure distances, and so we're using them to study dark energy. We use them to understand how heavy elements are formed and dispersed, and so on.
So cool, so cool. One thing I was really interested to ask you was, could there ever be a habitable planet orbiting a star and that star then subsequently went supernova? And what would happen to if there were life on that planet? What might happen to that life, and what would it look like to them? I mean, if our sun was big enough, was massive enough to go supernova, what would it actually look like?
Okay, so just like in our solar system, it takes time for light from our sun to reach us. Right? It takes 8 minutes. And so if our sun were to disappear, we would not, or blow up, we wouldn't know anything about it for 8 minutes. And then we would be, rudely surprised. We would see the sun, we would detect neutrinos coming from the sun, and there would be a lot of them, a lot more than we usually detect. And so alarm bells would go off immediately. And then we would get light. We would get a flash of UV light, and that would probably be the end of us. And then what used to be the star would plow into the Earth. And I'm not sure whether that would destroy Earth or would just give it a kick and send it flying out of the solar system. The solar system would disband anyway. All of the planets would get a kick once the shock, once the matter flew past them. They would all go spinning into space. Some of them might be picked up by other stars. Some would just go flying through the galaxy in a very lonely, dark way. I'm interested in the question of whether they would be disrupted, if they would be completely torn apart. There's a really one of the best episodes of Star Trek, The Next Generation. It's called Inner Light. And that's where Captain Picard is sort of spirited away to some village where he's told he's actually some completely different person who has a wife, and he ends up living a full life on the planet. He has a daughter. That daughter grows up to become a botanist, and she discovers that the star is becoming brighter, and it's affecting life on the planet. Plants are dying, and that's where the village kind of comes together and explains to Picard that that's how they died. Their star in that case became a red giant, and it became too bright, too hot to sustain, for life to still be sustained on the planet. And they knew this ahead of time, so they recorded this kind of simulation and sent it out into space so that anyone who would go through this solar system would encounter it and learn about them. And so that's all that remains of them at that point, those memories now lodged in Picard's head. So I thought that was one of the best episodes ever of Star Trek, and it was a really nice question to your answer of how would intelligent life deal with knowing beforehand that something like this would happen. And you would know, right? If you're around Betelgeuse, then you would know that something's happening. You would see your star start to go through these dying palpitations where every once in a while it would belch out some material, which would also probably not be very good for you. And so you wouldn't know exactly when. You wouldn't say, oh, Wednesday at 12 o'clock the world is coming to an end. But you would start wondering, what would happen to you grandkids, and and you would say something like, yeah, you know what, maybe I'll have dessert before lunch anyway.
Thanks for going through that with us. I mean, it's not a very appetizing prospect, is it? The prospect of being around.
We're not there. We're
No.
not there. Our sun is not going to explode. It will become a red giant.
Yeah.
The red giant might engulf Earth 4.5 billion years from now. Okay,
Yeah.
Don't worry about it.
So not something we have to worry about in the immediate future.
No.
Well, Or, it's been great talking to you today. Thanks very much for coming on the podcast and telling us all about the importance of supernovae. I sort of feel properly impassioned now about supernovae. I want to go away and read a bit more and learn a bit more. But yeah, good luck with the book when it comes out, Supernova. And thanks again for coming on the podcast and speaking to us.
Yeah, thanks. Thank you for having me on.